These are my questions for the Southeastern section of the Applied Physics Society, because I just got a lot of questions, and really it has to do with calories. It's all about calories and how calories work. And I've been studying this for a while, and it's supposed to be like combustion, like a human engine. We move like fire moves an engine. But is combustion really hydrolysis? Hydrolysis is the act of using water to cut a molecule. And as you can see on the right, that's what a myosin head looks like moving. That is a motor unit walking. So what happens in your muscles is similar to that. And as you can see on the left, the guy is using water, and that's because hydrolysis uses water. And so just to get to the question quickly, where is the energy stored after ATP hydrolysis? As you can see on the left, the active sites, they wait for the calcium to bind to the troponin in order to bind, and then they perform the power stroke. ATP binds to the molecule and it causes it to detach. Then it is hydrolyzed. This is where the energy is released, but it waits until the calcium binds. And that's just the fundamental question. If ATP hydrolysis is combustion, how can we wait for the calcium to bind for the troponin before using the energy produced? It doesn't make sense in physics if calories can't be real. They can't. It doesn't. So this is because of modern physics, we're able to advance our understanding of exercise and nutritional sciences. So the premise I'm bringing is that many problems and issues with modern exercise and nutrition can be solved with applied physics, like modern physics. That we have a huge obesity problem, $175 billion a year. That was an old statistic too. I don't know what it's up to currently. So I really want to encourage physicists to get into exercise and nutritional sciences, especially theoretical physicists. We can really use the help. I would like theoretical mathematicians, any computer scientists, all of you guys. If you love physics, get interested in exercise and nutrition because we need help. The leading modern theory is calories. It was invented in 1789 by Antoine. I always want to say Antony, like it's Anthony, but it's Antoine Lavoisier, and this elements of chemistry, or his treatise de blah blah blah. It was furthered by Carl von Voigt and Max Rubner in the 1800s. These are nutritionists, German physiologists, and it was brought over by W.O. Wilbur Atwater, after he studied with von Voigt and Rubner actually. So Atwater went to Germany and learned German specifically to study under von Voigt and Rubner to learn calories, and he developed this calorie system, what we call the Atwater system, where we correspond carbohydrates to 4 calories per gram, protein we do 4 calories per gram, and fat we do 9. Over here on this right side, you can see the heat, and then the percent available is supposed to be bioavailability. Look at all this complex math that they have to do for this. Anyways, let's continue about calories. So one of the things that the problem with calories is, look at these dates about when everything was finalized, pretty much, that this heat moves the body. But we haven't even gotten into the molecular age yet, the atomic age of all these scientists like Albert Einstein, Niels Bohr, Rutherford, Oppenheimer, Heisenberg, and J.J. Thomson. Thomson also discovered something in 1897. He discovered the electron in 1897. So Atwater had no idea that the electron, like there wasn't all these physical models like we have today about the electron and how the atom moves and works with itself. And so my claim is that calories are bad physics, and they don't account for modern physics past 1897. And this is the equation for essentially muscle movement. ATP is hydrolyzed with water, and it needs the catalyst ATPase, or will not hydrolyze in the right way to produce the mechanical energy that we get from ADP and inorganic phosphate, which is connected to oxygen molecules and energy. And remember, phosphate and oxygen are highly energetic. And the bottom equation is the combustion. We have fuel, oxygen, as well as some significant exothermic input, gives us the water, the CO2, and energy. And immediately you can see that the equations do not match. And as we know now, the water is released in the electron transport chain, and CO2 is released earlier in the Krebs cycle. And these products are multiple steps away from each other, not created together, not created from the same chemical products. And these are all discovered in different years. So you can see in red that the combustion of oxygen in fire was discovered in 1789 by Lavoisier. And we have different dates here, as early as 1929 for ATP and as late as 1961. That's 65 years ago, 60-something years ago, 63. And remember, like, the calories are supposed to be you burn like a candle. You burn calories, but you've never burned a calorie in your life. That's my argument. This all started with Lavoisier, Memoirs of Heat. He did calories are fluid, heat, matter, and friction combined because he couldn't agree on the theory, and he couldn't demonstrate which one was more correct. It wasn't until Joule came around in the 1840s, but he was the first to say respiration is like a burning candle and just demonstrate it mathematically and scientifically. Faraday, who's much more popular, lectures on the candle from 1853 all the way to 1861 was his last. He did 3 of them. He also emphasized that respiration is like a candle burning. And here we have the dates of the last one for Faraday. And you see 2 different dates for Lavoisier. The 1783 is where his memoirs on heat really came out, and 1789 is where he defined the calorie. And this is an explanation on how we figured out cellular respiration from Reddit, from Mike716. Pretty great explanation. I'll leave it here. I won't go over the whole thing, but if you want to pause it and read it, it's pretty interesting. So again, this is the main question: how is the energy stored after ATP hydrolysis? Because the energy is stored, and if calories are combustion, that doesn't make any sense. Because if it's fire, you can't really just contain it, right? You can't. If you put fire into a container and you try to hold it together, you get explosions. And you're not moving on a bunch of tiny explosions. You're really not. You're moving from chemistry, just like this fuel cell was such a great example of how energy can be generated from chemical reaction and not from always combustion. And that's what's happening in your body is chemical reaction. And this analogy to combustion is just not correct, because remember, we're saying it is fire. We're saying it is explosions, but it's not. It's just chemical. And this was really pronounced by Faraday. Faraday really helped to kind of nail this into everyone's psyche. And he was a very famous scientist, especially in his day. One of his most famous lectures were a chemical history of a candle. During Christmas time, over 3 different years, he would go around London to the Royal Society and speak on the history of a candle. There's a great thing online. I will edit in a clip of that in here. Go check it out from Engineer Guy. He goes over like the whole thing. Here's one of his quotes from the book. This is in the 5th lecture. And in this, the most important thing is what I highlighted in red, where he illustrates that respiration does not wait as a candle does. Well, in this part, he's talking about gunpowder, because gunpowder waits until it needs the right kind of heat. But in the other, where it's the gun cotton, it burns immediately. And so he's saying that it, like, when we breathe, it immediately gets converted into energy. All the air that we have is immediately converted as soon as it unites with the carbon. And so this was rewritten in 2016. And this is just to kind of illustrate how this is a modern understanding of calories and their applications and how we continue to misuse them today. And this just right here kind of nails it. Like Wikipedia, calories is a unit of energy that originated from the caloric theory of heat, which is Lavoisier's. But, you know, I always thought this was also true, that Joule's experiment, you know, disproved caloric theory, that we moved into mechanical theory, like mechanical heat. He's got a great beard, so it's got to be right. No, but for real, it's a nice beard. He did this in 1843, so even before Faraday. And I heard that when he gave this lecture that it was completely silent and no one knew what to say. Or maybe they didn't believe him. But Jesus, look at that price tag, $10,000. It's the original copy, but man. So my question is like, are calories actually real? And I really need help. And I'm hoping that this APS will be able to finally answer this question, because I really don't think they are. And if they're not, we need to take them away from nutritional sciences. Because remember, we have all these problems. And then there's just, my theory is that if we use don't use calories, we can solve a lot of these. If we understand like the actual mechanisms of the biophysics. Are calories real? They're created in 1789 by Lavoisier. He was the first one to create a calorimeter measuring the heat from an animal. He did this in the winter of 1782 with Laplace. This was disproven, I guess, in 1843 by Joule, right, when he did his experiments. But it was re-encouraged by Faraday, and he decided to give his beautiful lectures that really captivated people. I reintroduced between 1873 and 1888, I guess. That's when they say that Max Rubner, he first came up with it in 1873 and republished in 1883. I don't know when specifically Max Rubner, if he reintroduced it or where he got it from, but I'm just trying to follow this logical chain of events in these dates. And he's the one who originated the energy loss for the calories on each gram of food. And so it's not really the Atwater system, it's more of the Rubner system. But, Atwater went over there and, like an American, wrote a bunch of books, put his name on it. And here's something that is from the Principal Nutrition of Food. Heat and muscular power are forms of force or energy. Energy latent in the food is developed as food is consumed in the body. The process is more or less akin to that which takes place when coal is burned in the furnace of a locomotive. For the burning of the food in the body or the coal in the furnace, air is used to supply oxygen. When the fuel is oxidized, be it meat or wood, bread or coal, the latent energy becomes active. Or, in technical language, the potential energy becomes kinetic. It is transformed into power and heat. As various kinds of coal differ in the amounts of heat given off per ton, so various kinds of food and food ingredients give off different amounts of energy. That is, have different values of fuel in the body. And while some things are correct, like different foods have different values of fuel and material in the body, this is objectively wrong that food is used as fuel like coal in a furnace, because that is trying to say that this is combustion. And my entire point is that we continue to use calories, and calories infer and necessarily imply that our bodies use combustion. But again, the energy is stored after ATP hydrolysis, and that's in the electron. It's from the phosphate bonds. It's from the chemical energy. And so we don't need to blow up about this. We can just, relax like the electron and wait until everything lines up. And that's just the fundamental question. If ATP hydrolysis is combustion, how can we wait for the calcium to bind for the troponin before using the energy produced? They don't coincide. Calories can't exist. It goes against what all of these guys have worked for. It goes against what Jules apparently has made into a footnote, but is still around today. And one other thing I wanted to emphasize is that calories are a carbon-based theory of combustion. It has everything to do with carbon-based combustion. Because that's carbon plus oxygen, gives us our explosion. But ATP is something different. ATP is phosphorus. We didn't even really know about it until almost 100 years later after Faraday's lectures, like the structure of it. I bet you'd be impressed by it. But nowadays, we are all very familiar with this kind of graph, that the energy comes from the phosphate. So that's not from a carbon source, like calories in combustion suggests. So I'm just trying to understand what, can someone explain it to me? Because otherwise, I think I'm correct, and this is just not accurate physics. Calories just don't make sense. Because remember, how does this represent that? That's what we're trying to do in physics. We're trying to understand how this burning of these carbon sources translate into the phosphate fuel that we use in motion. It's just carbon energy and phosphorus energy. Not to mention that we don't even generate the CO2 and H2O in the same reaction as we do in combustion. Physiology is just much more complicated than that. It's a lot of different things going on. It's not just combustion. This isn't just fire and heat. And again, like just to go back to this post on oxidation, it's a great introduction into how we discovered aerobic respiration. And so it's not calories. It's just we got to get this out of our system. And so I appreciate you watching. I think that covers the essence of what I'm talking about. If you think you could break it down, tell me something I'm missing, or explain it what I am missing, so that way I can finally understand why we use calories at all. Please reach out. Please feel free to comment. Call me if you got my number. Call me, beat me if you can really reach me. Because helping each other out and developing science is a huge part of science. And we can really do great things if we do this. I really think we can help heal the world, change it, and move on. Cool. And that's it.